Hello everybody, today's presentation is on two-dimensional fare queuing for multi-tenant cloud services. It'll be presented by me, Nabil Belfki, and my partner, Rajiv Kumar. This is the paper. It was written by Jonathan Mace et al. It's backed by Brown University and Microsoft. Here's the agenda for today. First, I will go over the motivation, which consists of cloud computing, then multi-tenants, calculating request costs, and finally, fare queue scheduling. Next, Rajiv will go over the design of two-dimensional fare queuing, which has eligibility criteria as well, examples, request schedule under two-dimensional fare queuing. Rajiv will also cover two-dimensional fare queuing algorithm implementation, and then I will get into the evaluations, which consist of the metrics, known costs, and unknown costs, and finally I'll conclude. To comprehend what the authors convey in the paper, it is imperative to understand what cloud computing is first. Therefore, it is defined in layman terms as providing computer resources over the internet. These resources consist of cloud server, cloud storage, cloud network, deployment software, management software, and a hypervisor, as seen here. Here are some of the most known cloud providers in the industry. Most of you may be familiar with them. We have Microsoft Azure, Oracle Cloud, Google Cloud, IBM Cloud, and Amazon Web Services. And these make up the big players. This paper also deals with an architecture called multi-tenant. Some companies have their own data centers, making them single-tenant. With these cloud providers, on the other hand, all of these resources need to be shared by multiple tenants or corporations. The motivation behind this paper was a problem that arises with fare scheduling, or in other words, sharing these resources. Here we have an example that illustrates that. We have two tenants, one with a cost of 5 and one with a cost of 1. They both make requests to the cloud provider as seen. It is important to note that tenant 2 has to wait 5 units of time until tenant 1's request has been met to make another request. This may still happen even with multiple tenants, as we'll see here. When we add 2 more tenants into the mix, again with 5 and 1 cost respectively, this can still happen. This is called bursty scheduling, and it's not really fair because of the fact that it starves smaller requests out. An ideal situation, and what the paper and the researchers aim to do, is something called smooth scheduling, in which different request costs are prioritized on different worker threads. Worker threads can be thought of as these rows here. There can be many worker threads in a cloud provider's system. Next, the paper goes into detail about how to calculate request costs. It denotes start time as this, S being the start, R denoting the request, J is the current index of the request, so the request that has been made from F. F is the tenant. Next, finish time is shown as this. We have the size of a request, which is denoted as LJ of F. And we have the weight of the tenant, which is shown as phi of F, because not every tenant will have the same weight. This could be likely due to a paying model that favors certain tenants that pay more. The way that start time is calculated is either by taking the previous request's finish time, or if a request hasn't been made by that tenant in a long time, it takes the arrival time of that request into the system. The finish time, on the other hand, is calculated using the start time and adding the size of the request over the tenant. Here, to better understand this, we have an example on how to calculate start times and finish times and how to schedule requests. So let's look at that. We have 3 tenants, each with their own weights and costs of requests, size of requests. Here, for example, we can see tenant 1 has a request size of 4 and a weight of 4 as well. This can be broken down further, and with the start time, we're able to calculate the finish time. This is done by taking the start time plus the size of the request, as we said, over the weight of the tenant. So here, for example, tenant 3 has a start time of 1 and a finish time of 2 because it takes 1 second to complete the request. Here we show all of the variables again in case they were forgotten. But for simplicity's purposes, we have made it a lot easier to understand them by changing it to arrival being A and time being T, and these substitute finish and request over weight of tenant. Now, because tenant 1 arrives in the system at time 0 and it takes 1 second to complete, it will be scheduled first. As we can see here, though, tenants 2 and 3 arrive at time 1, but because tenant 3 has a shorter time to complete, it's scheduled first, and then because tenant 2 takes longer, it will be scheduled last. So that's how we calculate start time, finish time, and how we would like to schedule requests. There are actually many fair schedulers that exist. 2 very common ones are weighted fair queuing, which we saw from the previous example, and there's also worst case fair weighted fair queuing. These differ slightly in that weighted fair queuing looks at the request with the shortest finish time. That will be the one that will be prioritized and scheduled. Worst case fair weighted fair queuing is slightly different in that it adds another attribute on top called eligibility. What that basically means is that requests are only scheduled once they're deemed eligible, once they've entered the system, in other words. This will become more clear from the example that follows. So let's get into that. Here we have 2 tenants this time instead of 3, tenant A and tenant B. Along with that, we have a timeline for the arrival of the requests, and here we can see requests coming in from the tenants to our cloud provider. What's important to note here is that the first two requests from both tenants arrive at time 0, and then they both send out another request at time 1. A1 only takes 1 second to complete, while B1 takes 6 seconds to complete. Furthermore, the next two requests arrive at time 1, as we discussed earlier, and A2 takes 5 seconds this time to complete, and B2 only takes 2 seconds to complete. So how would these requests be scheduled based off of the previous two schedulers we discussed, weighted fair queuing and worst case fair weighted fair queuing? Well, we already saw weighted fair queuing before, and we said that it will choose the requests with the shortest finish time. So that would mean that A1 would be scheduled first, and then after that, B2 would be scheduled next. B2 has the second shortest finish time after A1. On the other hand, worst case fair weighted fair queuing will schedule B1 after A1. The reason being is because B1 is deemed eligible along with A1. The other two requests aren't eligible yet, and that is how worst case fair weighted fair queuing works. It needs to execute all the previous requests that enter the general processing unit, and once they have been completed, then it moves on to the next requests.
Thanks, Nabil. Hi all, I am Rajiv Kumar here and will take over to present the design and implementation sections of the Fair Queue Scheduler. As you have heard so far from Nabil, a system which allocates resources to tasks fairly and equally is called as a Fair Queue Scheduler, and it's especially helpful in cloud services where several tenants share resources. Our Fair Queue Scheduler solves the following problems if we think from design perspective. First, bursty schedules. Tenants with small requests can be starved of resources by tenants with larger requests. 2DFQ scheduler will ensure that all tenants have a fair share of resources regardless of the size of their request. Second, variable demand. Tenants may have variable demands on resources. The scheduler can split requests with varied cost across multiple threads to reduce the impact on other tenants. The third and very important, all or nothing behavior. WF2Q, which you have seen a popular Fair Queue scheduler, can suffer from all or nothing behavior, where a tenant either gets all of the resources it needs or none at all. The 2DFQ scheduler addresses this problem by allowing requests to be eligible for different amounts of time across different worker threads. Now let's see how 2DFQ algorithm works. So the basic idea is to divide the multiple threads into two groups, the small and the larger request threads. Then estimate the size of the request when it first comes in. A smaller request will be placed in a small request thread. Larger request will go in large request thread. 2DFQ scheduler then schedule the request in each thread in a fairly manner. I will explain eligibility criteria in this slide, which I think is the most important concept if you are trying to understand how this fair scheduler works. As you are seeing on this slide, there is a formula, but to detail more about this formula, let me start with the different variables which you see here. You see SRJ, which is nothing but the start time for any request RJ. J is an index. Then you see IJ, that is the length of the time between each eligibility interval. A small n is the number of threads in the system. The 2DFQ eligibility criteria, as you have heard so far, mention that a request RJ will be eligible on thread I at a time SRJ minus I divided by n multiplied by ij, the formula which you are seeing here. That is, the request is eligible on thread I at a time that is staggered by I by n multiplied by ij from the start time of the request. Let's make it more simpler to understand, and I will go deeper. For example, let's suppose we have a system with two threads. A request RJ with a start time of 100 will be eligible on thread 0, and on thread 1 at virtual time 100 and 105 respectively. The staggering eligibility interval helps us to ensure that all requests have an equal chance of getting processed, even if there are of the variable sizes, dynamic sizes to say. Some of the requests could be very small, some of the requests could be very large. So we want to reduce the impact of tenants with variable demands through this eligibility criteria. Further, let's see how this 2DFQ eligibility criteria works. When a request RJ is submitted, the algorithm will calculate the eligibility time on each thread. The request will be placed on each thread with eligibility time as the priority. When the thread is free to process the request, it selects the request with the highest priority from the queue. If there are multiple requests with the same priority, and you know it can happen that you will have multiple requests and with the same priority, now what the dilemma is what to do. That point of the time, the threads select one of the request at random. This process ensures that all requests are processed in a fair way, regardless of the size of the demand of other threads. Now, in the practice, the 2DFQ eligibility criteria works. Let me explain more from the tenants and one more example here. Let's say we have the tenant A and the tenant B. Tenant A has a large number of a small request, while the tenant B has a small number of large requests. What will happen without the fair queue scheduler? The tenant B, which is of large request, could easily take up all the resources, and the tenant A, which is of a small request, could end up waiting forever, or at least till the time tenant B is over. Its all requests are processed. Now, with this 2DFQ eligibility criteria, the formula which you are seeing on this screen, tenant A, a small request, will be staggered across the different threads, which will ensure to have an equal chance of getting processed as the tenant B, which is having the larger request. Let's consider a system with two threads, W0 and W1, and a request RJ with a start time of 4 and a length of 2. As you have seen in the previous slide, with the formula Srj minus I by n multiplied by Ij, the eligibility criteria states that the request eligible in based on the formula. Now here, as you see, the very first, the eligibility time for Rj on W0 thread, if you put into the formula, and it gives you 4. While in second, the eligibility time for Rj on W1 thread, like putting everything on the formula, that gives us 3. So Rj will be eligible on W0 at time 4 and on W1 at time 3. In this example, let's consider a system with 4 threads, that is n is equal to 4, with the request Rj, Srj is equal to 10 and Ij is equal to 4. Now this eligibility time for the 4 threads, W0, W1, W2 and W3 are calculated as you are seeing on the slide. W0 will become 10, W1 9, W2 8 and W3 is equal to 7. So it's clearly visible that Rj, that's a request, becomes eligible earlier on thread with higher index. Let's do a quick recap what we have seen in previous slides. 2DFQ staggers a request eligibility time across the thread. That is, a request might be eligible on one thread sooner than on another thread, which is helping a fair chance of a request getting processed regardless of its size. Second, high index thread can run a small request sooner than low index thread. This means to say high index thread have shorter eligible times for a smaller request. Third, partition by size. Because the staggered eligibility times, thread sorts request by size. That is, the high index thread tend to service a small request, while the low index thread will be processing service with a large request, which ultimately helping and ensuring that a small requests are not starved of resources by large requests. In this slide, let's see request schedule under 2D-FQ. We have a scenario here where we have two worker threads, W0 and the W1, which are being shared by 4 tenants A, B, C, and D with the backlogs. The small requests size 1 are made by tenants A and B, while the large requests size 4 are made by tenants C and D. A and B's second request won't be accepted on W0 thread until T is equal to 2, but they will be accepted on W1 thread at T is equal to 1, which you are seeing in the diagram. C1 is scheduled for W0 by 2D-FQ, while A2 is chosen for W1 thread. Following that, A and B continue making requests on W1 in turn. The very first step in 2D-FQ algorithm is to calculate the eligibility time of the request on each thread. Once eligibility time is calculated, the request will be placed in the queue, where here you see in the flow. You initialize the queue in the first step, checking the request in the second step whether the request is the new. If the request is the new, you move to the third step, you enqueue the request. Then in the fourth step, you check whether thread available, yes or no. If the thread is available, you dequeue to the thread. Then in the sixth step, you refresh the queue. Seventh, complete request, and that's where the process ends. So very simple flow, and this flow will be applicable for any fair queue scheduler. And as I mentioned before, eligibility time calculation is the most important from the 2D-FQ perspective, and then putting this in the flow. Now let's talk about some more about the 2D-FQ implementation based on this research paper. Now we see that 2D-FQ will be very beneficial for the cloud services, and it can balance the service provisioning to the different tenants. The pros definitely is handling variety of task sizes. It could avoid the delay of the smaller tasks by bigger tasks. Also from the pros, it reduces the burstiness and very advantageous for quick jobs. So basically it's providing a balanced approach for servicing various tenants and at the same time supporting fairness. The cons which I see, that we should have a good understanding on the estimation of the task duration, which might be challenging sometimes. Also, 2D-FQ penalize tenants which is having dynamic request sizes, dynamic task sizes, or you can say task sizes fluctuating. And 2D-FQ will always believe in such situation to have the big jobs, which could result in the lack of resources. I think this paper could be further expanded on unpredictability or the varying size, the dynamics, and also that could guarantee fairness of the variable demand. And I believe the further investigation and modification for the various cloud services type could increase the applicability of 2DFQ algorithm.
That was a great explanation, Rajiv. Thank you for that. Next, it's time to enter the evaluation part of the presentation, where we look at the author's experiments and how they compared. To begin, before showing the results, we need to go over the metrics that were used in these experiments. Those metrics were service lag variation, service rate, latency, and the Gini index. Service lag is the difference in how long it should have taken for the request to process and how long it actually took. Standard deviation of that is the service lag variation. The service rate is work done in 100 ms intervals. Latency is the time it took from when the request entered the queue to when it actually finished processing. And the Gini index is an instantaneous measure of scheduler fairness across all tenants. That can be thought of something similar to a rating or ranking of tenants. There were two variants of experiments that existed. The first part was known costs, and the second part was unknown costs. So let's begin with the known costs variant that the authors took. This experiment was called the expense request. There were actually two here. There was another experiment as well that had real-world data. This had synthetic data. And both of the experiments had 16 worker threads, n small tenants, and 100 minus n large tenants. They increased the size of large tenants as the experiments progressed, therefore hinting at expensive requests. Some of the findings from the experiments were, if you see the first part of this graph that denotes the service rate, worst case fair weighted fair queuing had large oscillations denoted by the blue. Worst case queuing also had oscillations, and the important thing to note is two-dimensional fair queuing didn't have much, so the service rate was quite consistent, and that can be seen from the red line. The same goes for service lag. Two-dimensional fair queuing had none. Weighted fair queuing had higher amounts of service lag, and worst case fair weighted fair queuing had below zero because of the nature of how that scheduler works, and it's always backed up. Here, we see again how they fare and how requests were scheduled on each worker thread. Each row denotes a worker thread. And again, there were 16. What can be seen from weighted fair queuing is that it still has that bursty schedule in nature. If we look at the beginning here, you can see that many large requests were processed at the same time, therefore starving smaller requests. Large requests are shown as dark blue. Smaller requests are shown as light blue. This becomes even more evident when we look at worst case fare, weighted fare queuing, where it can be clearly seen that there is bursty scheduling. It tends to oscillate between large requests and then smaller requests. And it can also be seen that two-dimensional fare queuing here has smooth scheduling. And as we discussed earlier, large requests and small requests are separated on different worker threads. In this part of the graph, we can see that the top 8 worker threads have smaller requests and the bottom 8 have larger requests. It can also be seen that some small requests are in the worker threads that are designated for large requests. That is okay. That's to maximize efficiency. The scheduler will sometimes do that if there is no other large requests that can be scheduled. The same goes for smaller requests too. We can see a large request in worker thread 9. Here, we see the standard deviation of the service lag starting from 0 expensive tenants, as we said, all the way up to 100. This was changed over the course of time. Weighted fare queuing had linear standard deviation of service lag. The more that expensive tenants and requests were introduced, worst case fare weighted fare queuing plateaus at their worst case fare bounds because of the nature of it, and two-dimensional fare queuing tended to have low differences in standard deviation. Here we see the second portion of the experiment, which was on Azure storage. This is production data, real data in the cloud provider. For this part of the experiment, there was 32 worker threads instead of 16. It was chosen from 250 random tenants across 50 servers, and request costs varied from 250 to 5 million. Here we can see from our first graph, again, weighted fare queuing is denoted as yellow, worst case as blue, and two-dimensional fare queuing is red. By looking at the top part of the graph, again we see that two-dimensional fare queuing is consistent, is the most consistent when it comes to service received. Weighted fare queuing has high service lag, and the others have less. Two-dimensional fare queuing barely has any service lag. So the experiment that dealt with synthetic data is quite similar to the one here that deals with real-time production data. Not that many differences. And then down below we can see the Gini index of the tenants and how they were rated. Here we have another graph, again denoting small costs and large costs. Here we can see the scale at which these costs are colored. 10 to the 7th is dark blue, and then down at the bottom we have 100 request size. Looking at weighted fare queuing, they're quite dispersed. There tends to be starvation of smaller requests in the middle of the scheduler. Again, here we see some clusters in worst case weighted fare queuing. And with two-dimensional fare queuing, we have a smooth scheduler again. And there's no bursty behavior. Here we have the second variant of the experiment. This went over unknown costs. where request costs had to be estimated, as we discussed earlier, as Rajiv had said. For this part of the experiment, there were 300 random tenants picked. There were differences in unpredictability. The experiment began with 0% unpredictability, then went on to 33% and 66%. Here we have results from the experiment. Again, they're denoted as the same. The important thing to note here is in the top portion with 0% unpredictability, these results are quite similar to the previous experiment that we had. Two-dimensional fair queuing is consistent again. There are oscillations in worst-case fair queuing and weighted fair queuing. Here with 33% unpredictability in tenants, two-dimensional fair queuing still fares well between the others. Even with 66% unpredictability. It's important to note, though, the more unpredictable the tenants become, the more difficult it is for service to be consistent. And that is because many of the tenants will be marked as large tenants, and it's harder to estimate them. Here again, we see how these requests were dispersed upon the worker threads. The sizing is the same and the coloring. Here with 0% unpredictability, we had the same. With 33, they tend to be more dispersed, and then when we get to 66% for two-dimensional fair queuing, it tends to drop off, and a lot of larger requests will be scheduled in the smaller worker threads and vice versa. To summarize the evaluation, when request costs are known, both synthetic and real-world workloads, two-dimensional fair queuing provides service to small and medium tenants that has 1 to 2 orders of magnitude reduction in service lag variation. When many tenants have expensive requests, two-dimensional fair queuing maintains low service lag variations for small tenants. When request costs are unknown, two-dimensional fair queuing, when it's unpredictable, reduces service lag variation by 1 to 2 orders of magnitude for small and medium tenants. With increasingly unpredictable workloads, two-dimensional fair queuing unpredictable improves tail latency of predictable tenants by up to 100 times. And finally, across a suite of experiments based on production workloads, two-dimensional fair queuing estimated improves for predictable tenants up to 198 times. So it is an improvement over weighted fair queuing and worst case weighted fair queuing as seen from those results. Finally, we come to the conclusion. Let's go over what we discussed today. First, we define what the cloud and multi-tenants are. Then we illustrated the challenges dealt when scheduling requests among tenants with small and large costs executed in parallel on many threads. Then we identified an efficient scheduler, two-dimensional fair queuing, for achieving smooth schedules. And finally, with this scheduler, small requests won't be starved out by larger ones under most circumstances. Thank you all. If you have any further questions, feel free to reach out to us. My email is nab72@ngit.edu, and Rajiv's is there as well.